So for the final talk of this session, for the afternoon coffee break, we have Zhou from Yale, and he's going to tell us about tap-free energy. I don't actually know what that is. It's the national airline of Portugal, I guess.
That's right.
And some other things, so take it away.
Great, okay. Good afternoon, everyone. Thank you for coming. Thank you to the organizers for organizing this wonderful workshop. So it's my first time at Simons. And when I was watching videos of what happens at Simons to prepare for this talk, every video I saw was Blackboard lectures, and so I thought everyone gave Blackboard talks. So it was too late for me to change it at this point. So I'm going to give a Blackboard talk. I'm going to talk about variational Bayesian inference in high dimensions. This is joint work with Andrea Montanari and Song Mei, both of whom are here in the audience today. Okay, so we're going to talk about Bayesian inference. I'll consider a very simple Bayesian model, which is the following. We're going to observe an m by n symmetric data matrix. I'll call that Y. So Y is in R by m by n and symmetric. And the model for Y is that it's going to be the sum of a rank 1 signal component. I'll call that lambda over n times XX transpose. And then plus some additive Gaussian noise W. All right, so here X is a signal vector. It's an Rn. And we're going to do Bayesian inference, so we'll put a prior on X. The prior that we'll put is that, let's say the signal vector belongs to the hypercube, so every entry of X is plus minus 1. And we'll just consider a uniform prior. So each entry is with probability of half equal to plus 1, and with probability of half equal to minus 1. This matrix W here is our noise. This is symmetric noise we'll consider. And so as a simple model for the noise, we'll assume it's Gaussian. So above the diagonal, Wij for I bigger than j, we'll assume, let's say, it's normal with mean 0. And the scaling that I'll use is variance 1 over n. Below the diagonal is just a symmetric reflection of what's above the diagonal to make it symmetric. And then on the diagonal, it doesn't really matter what I put here because there's no signal on the diagonal. But for certain reasons of convenience, we can consider Wii to be normal 0, 2 over n, let's say. And these are independent. So these are IID, these are IID. Okay. And an observation that we can make regarding the normalization I'm using in this model is the following. Can you guys see if I write down here in the back?
Yes.
Okay. So the normalization in this model, if I look at what is the spectral norm of this rank 1 signal, it's lambda over n XX transpose. X has squared Euclidean length n, so the spectral norm of the signal component here is lambda. For this noise matrix that I've constructed, the spectral norm of W is approximately 2 with high probability. And so you can think about lambda here as representing a signal to noise parameter. And so what we'll assume throughout this talk for lambda is that, so we're going to consider asymptotics. Lambda is going to be a constant as n goes to infinity. But we'll need to assume it's sufficiently large. So sufficiently large. And what I mean by that is that it's larger than some universal constant lambda naught. Okay? Okay, and so I want to talk about Bayesian inference in this model. We have a prior on X.
So the rationale for 2 is some scaling that we'll see later?
It doesn't really matter. I can set it to be 0. The rationale for 2 is that this is then a Gaussian orthogonal ensemble that's rotationally invariant. For certain formulas involving the likelihood, it'll be convenient. Okay, so I want to do Bayesian inference in this model, and what that means is the following. So I want to be able to understand what is the posterior distribution of my signal vector x given this observed data matrix y. And for example, a common task is that I want to, for instance, compute the expectation of some simple function of x, let's say, conditional on my observations y. All right, so let me make this actually even more concrete. Let's consider a very specific estimation problem. So suppose that I want to estimate this rank 1 signal matrix, and I'll call that big X. So big X will be little x transpose. So my goal is to estimate this, and let me write down the loss. So the risk function I want to consider, let's say, is the expectation of the Frobenius norm error squared. So x hat is my estimator minus the truth squared Frobenius norm difference, and I'll normalize this by 1 over n squared. Okay. So let me consider this as my inferential task. And so if this is what I want to do, then by standard classical Bayesian decision theory, I know what my optimal estimate should be. The optimal estimator should be given by the Bayes estimate. So x hat Bayes, I'll call this, is just the posterior mean, the expectation of XX transpose given y. Okay. So this optimal estimator has been studied before, and in particular in a paper by Deshpande, Abe, and Montanari. 2016. And what's known about this estimator is the following. If I look at the actual Bayes risk that's achieved by this estimator, so the expectation of 1 over n squared times this Frobenius norm error squared. So this is the true Bayes risk. This expectation is over both this prior on x as well as my estimator. All right, so this Bayes risk, asymptotically as n goes to infinity, converges to a certain constant depending on the signal-to-noise lambda. And I'll call this constant xi of lambda. Okay, so what's known is that there are two regimes. If lambda, the signal-to-noise, is less than or equal to 1, then I can't do any sort of interesting form of estimation. This xi of lambda would just be equal to 1. And this is the error that you would get if you were to just estimate 0. This is the trivial estimator. Right. And for any signal-to-noise lambda bigger than 1, you can do some form of a non-trivial estimation, and this xi of lambda will be strictly between 0 and 1. So it can achieve some correlation with the truth. Okay. Fine, so this is fine. So my goal is to be able to compute, posterior expectations of quantities such as this. And of course, the difficulty in Bayesian inference is that exact computation of these kinds of posteriors are believed to be intractable. Right? If I were to do a naive computation of this posterior, I would need to, for example, sum over 2 to the n points on the vertices of my hypercube to compute this expectation. So what I'm going to talk about today is what's known as the variational approach to Bayesian inference, so variational Bayes or variational inference. To describe to you what this is, let me call the true posterior, so let me denote that by pi of x given y. This is the true posterior that I'm interested in. And let me call script p the class of an approximating class of probability distributions. Script p will be the class of all product measures on the cube. So all product distributions on plus 1 minus 1 to the n. And what this just means is that every single coordinate, each of my n coordinates is an independent Bernoulli variable, plus 1 or minus 1. Okay? And so corresponding to this class script p, so if I take any probability distribution p and p, because all the coordinates are independent, I can parameterize this distribution by just what is the mean of each coordinate. In other words, if I were to sample a vector x from p, what is its mean? The expectation of x. So let me call this a vector m. M sits inside the solid cube in n dimensions. And the variational approach to inference, so the most commonly used method of variational inference is what's oftentimes called mean field variational inference. And in the mean field approach, what we want to do is we want to find the distribution p in this class of product measures, which minimizes the KL divergence from p to the true posterior pi of x given y. Now, if I were to write out what is this KL divergence in the particular model I wrote down, we can write that in terms of this mean parameter here. And what this becomes is we want to find m hat, which is the minimum over the solid cube of the following functional. I'll call this the mean field free energy. And this functional takes the form minus lambda over 2n, m transpose ym. This is sort of the energy term. And then minus an entropy term, 1 over n, sum I equals 1 to n, h of mi. H here is the binary entropy function, so h of m is minus 1 plus m over 2, log 1 plus m over 2, minus 1 minus m over 2, log 1 minus m over 2 is just the entropy of a Bernoulli random variable, plus 1 minus 1 with mean m. Okay? And so the mean field approach is I want to find this distribution p, or equivalently this parameter vector m that minimizes this objective. Okay? So if m hat minimizes this objective, then it has to satisfy the first order stationarity condition, which is that the gradient of this mean field free energy at m has to be equal to 0. Okay. And if I differentiate this and compute this gradient, this I can rearrange as the equation m equals the hyperbolic tangent of lambda times y. So this is the mean field. Okay, so as a sort of consequence of our main results, the first theorem I want to state is the following. So what we show is that actually this kind of approximation is not correct asymptotically as n goes to infinity for this model. And let me be more precise. So what I mean by this is the following. Let m hat be any critical point, so be any point satisfying this first order condition. So it satisfies that the gradient of the mean field free energy at m hat is actually equal to 0. And let me construct from m hat an estimate of my rank 1 signal. So let x hat be m hat transpose. Because the coordinates are independent under my posterior approximation, this is also equal to the expectation under this p hat of xx transpose, ignoring some details on the diagonal, which are not important for this talk. Okay, so the result is the following. If I consider, so for lambda bigger than this constant I mentioned earlier, for lambda bigger than lambda naught, as n goes to infinity, the squared difference, so if I look at the expected squared difference between this x hat constructed here and the true Bayes estimator, x hat Bayes, for Frobenius norm squared, this in fact does not go to 0, so I don't get an accurate approximation of the true Bayesian quantity I'm interested in. And as a consequence, if I were to look at the Bayes risk of this estimator, x hat minus the truth, xx transpose for Frobenius norm squared, this also does not go to the optimal Bayes risk, which I called psi of lambda.
Is that 1 on n or 1 on n squared?
No, sorry, 1 on n squared. Both of these are 1 on n squared. Thank you. Okay, so what we study instead in our paper is a different approach to variational inference. It's called tap variational inference. And in tap variational inference, what we consider instead is a different energy functional. So consider instead m hat, which minimizes what I'll call the tap free energy, arg min over m, over minus 1, 1 to the n. This is m belonging to this set. I'll denote this by f tap of m. F tap of m will be the mean field free energy, f mean field of m, plus a certain correction term, and the correction term is lambda squared over 4, 1 minus q of m, quantity squared, where here q of m is the mean of the squared entry of m. So I'm going to consider this alternative minimization problem. And again, if m hat is a minimum of this, then it has to satisfy the first order stationarity condition. Yep.
Yeah. So this theorem is for any lambda bigger than lambda 0, or
for any fixed, no, for any fixed lambda bigger than lambda 0. I don't have a quantitative.
So even for large lambda, the problem becomes easy.
That's right. Yeah, we still have this problem. Okay, so if m hat were to minimize this tap free energy, it also, yeah.
Is there a reason why the risk over there, the goal that you've written there should be achievable by a product distribution?
Yeah, there's some intuition for this, which is that in this model, the posterior distribution, the coordinates are approximately independent in some sense. They're independent in the sense that if I look at a finite dimensional marginal of the posterior distribution, then as n goes to infinity, those in that marginal, they're actually, okay, I take that back. There's a sign symmetry in the specific model I wrote down, but up to a global plus minus 1 sign, you have a certain amount of independence that you expect in the posterior, which is why we might believe this kind of approximation to be true. But what I'll try to show you is that it's not true in the sort of joint sense. It's not true that if I look at the joint distribution of all n variables in the posterior, I have enough independence, and sort of that's where this tap correction is going to come from.
Is lambda in the loss function the true lambda?
Yeah. The lambda in the loss function is true lambda. We're going to assume that lambda is known. If you don't know lambda, you can just estimate lambda from the largest eigenvalue.
What does TAP stand for?
Okay, I was going to write that down. Okay, so tap, right. So if m hat optimizes this, then it satisfies the first order condition that the gradient of f tap at m hat has to be equal to 0, or at m has to be equal to 0. And if you write out what is the stationarity condition here, you get the equation m is equal to the hyperbolic tangent of lambda times ym minus lambda squared 1 minus q of m times m. Okay, so this equation here first appeared in the statistical physics literature in the study of what's called the Sherrington-Kirkpatrick model for spin glasses. This equation appeared in a paper by Thales, Anderson.
The camera's not going to see what you're about to write.
Okay, thank you. No, it's okay, it's okay. I'll write over.
Multi-million dollars.
This is very
Okay, so TAP stands for Thales Anderson Palmer. It's a paper about the SK model in '77 that first introduced that sort of fixed point equation. Okay, so the theoretical result that we have about this is that this somehow fixes this problem of mean field base. So let m hat, again, let's say m hat is the global minimizer, so arg bin over m of this tap free energy.
Excuse me, should I think of tap as a different divergence or different posterior?
You should think of it as a different criterion under which you're under which you're trying to estimate the.
So you keep the posterior to the product, but you.
Yeah, I'm still going to make a product approximation to the posterior, but I'm
you
going
have to change the divergence, right?
That's right. It's not a KL divergence anymore. It's a sort of.
Can
It's
you
a.
motivate it? What kind of divergence?
I don't know if it comes from a.
It is still the KL divergence. And the minimizer should still be the KL divergence.
Okay.
So-called.
As n goes to infinity. I see.
Okay, so what was I going to say? Oh yeah, okay. So let me consider the global minimizer of this functional m hat, and let me define the estimate of the signal matrix x hat to be m hat transpose. Then we have the following result: for lambda is bigger than lambda naught as n goes to infinity, we get the correct behavior. So if I look at the expected square difference between x hat and the true Bayes solution, x hat Bayes, that this does go to 0 as n goes to infinity. And as a result, if I look at the Bayes error, the Bayes risk achieved by this estimator, so minus the truth, this does go to this optimal risk. So this is the problem. Okay, that's fine. And then if you look at the form of this functional I wrote down, it's not a convex optimization problem. So a priori, it might not be clear as to whether we can actually efficiently compute this estimator in practice. We don't give a definitive answer to this, but we give pretty strong evidence in favor of the fact that this is computable. We believe it should be easy. So the specific result that we show in our work is that furthermore, this statement that I wrote here is going to hold not just for the global minimizer, but this holds for any critical point. So any m hat satisfying that the gradient is equal to 0, provided that the value of this function is sufficiently small. So and that the value of this tap energy at m hat is less than a certain constant, which is we give a bound of negative lambda squared. So this bound, you can check that if lambda is big enough and you do some kind of a spectral initialization, you're going to fall in a region of the energy that's less than this. And what this suggests is that if you run a gradient descent from there, it should probably converge to m. Although we don't do an actual numerical analysis of the convergence of gradients.
This is gradient equals 0?
This is the gradient equals 0. Thank you.
Ideally, lambda 0 should be 1.
I mean, we want to get some kind of recovery whenever lambda is bigger than 1. I don't know whether I don't know whether this picture of the local landscape is going to hold all the way down to lambda equals 0. Let me just mention that. So we're not the first work that considers this equation star to do inference in this Bayesian setting. If you view this equation that I marked over there, the tap equation star, as a sort of fixed point equation where you update m iteratively, that's what's called an approximate message passing algorithm. So there's a connection between star and the existing literature of AMP algorithms. And some of the early rigorous work in this area was done by Bolthausen in 2014. And the specific model was studied also by Deshpande, Ape, Montanaro, paper I mentioned. Okay, but the flavor of the result that we prove is a little bit different. I think we're the first people to actually analyze the actual critical points or the actual stationary points of this iterative algorithm for finite n.
So I have a question. If you want to lower the variance of the estimator, what can you play with?
If I want to lower the variance.
So for finite n, not infinite n, there is nothing to...
You mean the fact that this doesn't converge to 0, let's say?
Well, even when it converges to 0, you can, for finite n, it's not 0.
Yeah, no. So we're in an asymptotic regime where you're not going to be able to get a consistent estimate because the signal to noise is just bound. Like if lambda goes to infinity, you're going to be able to get a consistent estimate. And you can study maybe rates of estimation, that kind of regime. We're studying a regime where the best thing you can do is some constant level of risk. And asking the question, can we really achieve the constant level of risk that the Bayes estimator should be able to achieve?
Can you explain a bit more about the
Yes, okay, great, thank you.
Is it a sort of regularization?
It's, okay, let's see. So what I wanted to do in this talk was two things. One is I wanted to go through some kind of a derivation or some heuristic explanation of where this tap correction comes from. That's not really a part of our work. It's a very classical statistical physics derivation, but maybe it'll be useful for the audience to see. And then I'll say a few things about how we prove this result. Okay. So maybe that'll address your question, Edgar. Okay, so the first thing that let me do is to kind of explain the origin of this correction in the tap free energy. So to explain the origin of this correction, I'm going to start with the posterior distribution, pi of x given y. And because I have a uniform prior, this is just proportional to the likelihood of y around the signal. So it's the Frobenius norm difference of y minus lambda over n, x transpose squared. And then you can check that there's a constant here, which is n over 4. Okay. If you expand the square and drop terms that don't depend on x, then this is proportional to the exponential of lambda over 2 x transpose yx. So what I want to do is to write this posterior distribution by singling out a particular coordinate of x. So let me write this as the distribution over xi, the ith coordinate, and then x super I will denote the vector of m minus 1 other coordinates. So let me single out this coordinate and let me write this, this posterior density also by singling out a coordinate. So I can look at the part of this that depends on I. It's lambda times xi times the sum j does not equal to I of yij xj. And then plus the rest of this stuff that doesn't depend on xi, so it's lambda over 2 x super I, and then what I get is the minor of y, the m minus 1 by I minus 1 minor of y with the row and column I removed, times xi. So I can write the density in this way and single out this coordinate. Now what this shows is that the dependence of xi on the remaining coordinates in this model is only through this term here. This term, let me give it a name. The traditional name is hi. It's called the cavity field. And so what I can do is I can write down what is the marginal law of xi and hi given y. And to get this marginal law, I need to sum over the remaining m minus 1 coordinates. And so what this looks like is the exponential of lambda xi hi. And then times some distribution over hi that's induced by this part of the law, right? So times some law that I'll call pi super I of hi given y. And what pi super I is this is the marginal law of hi under the distribution pi super I of x super I given y super I, which is proportional to x of lambda over 2 xi transpose yi xi. So what this distribution represents is I've removed the ith coordinate from my model, right? I'm looking at a model with m minus 1 parameters, and this is the corresponding posterior there. And whatever law that induces on xi, I then define this variable hi, and this is my joint law of xi and hi. So we can let m be the posterior mean of x. And if I observe from this equation, h is given by y times x minus some details on the diagonal. So we have h equals y times x, and if I look at the expectation of h given y, this is going to be y times m. So you can view both of these forms of variational inference as making some kind of an approximation to this distribution on hi, which is called the cavity distribution. So if I look at mean field variational inference, the kind of approximation it's making is just replacing this by a constant, right? It's going to ignore the fluctuations of this variable hi and just make the approximation that pi I of hi given y is approximately some delta mass on a coordinate ui. If I make this kind of a constant approximation, then what I get from here is that ym, which is the expectation of h given y, well, h is just a constant, so this has to be mu. And what I get from this first equation is that m is the expectation of x given y. I can compute what is the expectation of x given y in this model when h is equal to mu. And I get that this is the hyperbolic tangent of lambda mu. If I plug in mu from up here, I get the hyperbolic tangent of lambda times ym. And this is exactly the mean field equation. So now the difference between this and TAP is that in the TAP approximation, we're not going to ignore the fluctuations of hi under this cavity distribution. Instead, we're going to try to take that into account. But the way we'll take it into account is that we'll try to make an approximation that the remaining coordinates xj's are approximately independent under this cavity log pi I. And if we believe this kind of approximation, then what this suggests is that hi, being the sum of these independent random variables, might have some kind of a limiting Gaussian behavior for large n. So the approximation that we're going to make for this distribution, pi I of hi given y, is that it's approximately normal with some mean mu I and some variance sigma I squared. Now under this approximation, our joint law of xi and hi given y, this is what will be proportional to the exponential lambda xi hi times the density of this normal. Let me call that dn mu I sigma I squared hi. And under this, I can again exactly compute what are the marginal means of x and h. So I have that ym is equal to the expectation of h given y. If I compute this Gaussian integral, I get an exact form. I get mu plus lambda sigma squared times the hyperbolic tangent of lambda mu. This equation is interpreted entry-wise, so mu I plus lambda sigma I squared, etc. And I get x, I get m, which is the expectation of x given y. I can also compute the mean of x under this approximation, and what I get is still tan h of lambda times mu. And if I substitute mu from this first equation down into the second one, I get tan h of lambda ym minus this correction term here. I get minus lambda squared sigma squared, and then tan h of lambda mu is just n. So I get a fixed point equation of this form, where what we've seen is that if I try to account for the variance of this variable hi, then I need to subtract a certain correction term in the mean field equation. And finally, so what should this correction term be? Well, we have that sigma I squared should represent the variance under this cavity field of hi given y. And if we believe that these xj's are approximately independent, then what this should be is just the sum j does not equal I of yij squared times the variance under the cavity field of the individual xj given y. The xj's here are plus minus 1, so this is 1 minus the expectation of xj given y squared, and we'll make this approximation that's roughly 1 minus mj squared, where mj is just the mean of x. And finally, the last observation is that this variance of xj given y, this is really given yi, the minor with row I and column I removed. It's independent of the ith row of y. And so because of this independence, when we look at the sum, we expect some kind of a law of large numbers phenomenon to kick in, where this is approximately, for large n, the sum over j. The expectation of yij squared is roughly 1 over n times 1 minus mj squared. And this is exactly this quantity 1 minus q of m. So we get that the variances for each coordinate is roughly 1 minus q of m, and once I plug it into here, I get this type equation. So you can view this as a sort of correction that accounts for the variation in this cavity field. So the remaining time that I have, so this is not really the approach that we use to prove the result that we have, but I wanted to show where this comes from. And in the remaining 10 minutes or so, I want to give an outline of what is the strategy by which we proved our main result. So our result was a result of the following form. If I take any critical point of this tap free energy that's below a certain value of the function, then that should give me an accurate approximation to the true base posterior of this model. Right? That was the result. Okay, so the proof of this result, for simplicity, let me just assume without loss of generality that the true vector x is just all ones. This is just for notational convenience. And what I'll define is for any probability distribution. For any probability distribution, let me call it rho, on this interval -1 to 1, I'm going to define 4 linear functionals of rho. So I'll define q of rho is the integral of x squared d rho. I'll define m of rho, which is the integral of x d rho. We can define a of rho, which is the integral of x times the hyperbolic arctangent of x d rho. And we'll define h of rho, which is the integral of this binary entropy function h of x d rho. I can accumulate all 4 of these into a single vector. So let me define t of rho to be q, m, a, and h. And you should interpret this as a certain projection of this measure rho onto R4. And I'm summarizing the distribution by just 4 numbers. Okay. For a vector, so for a vector m in Rn, we're going to identify this with its empirical distribution of its coordinates. So identify m with what I'll call rho n, which is the empirical law of the coordinates. Right? So 1 over n sum over I of the delta mass on xi. And I'll use the notation q of m is the same thing as q of rho n, etc. So in particular, q of n would be the average squared entry of m, which is what I wrote down before. This is just a notational identification. So one sort of trivial but important observation is that if I were to look at the risk that we're interested in, or the loss function, so if we look at this error, 1 over n squared, mm transpose minus xx transpose for Frobenius norm squared, this is the loss that I defined. This loss is actually just a function of this projection of m, right? So if I expand out this square, in particular, you can check that this is 1 plus q of m squared minus 2 m of n squared.
Just a question, for the rho there, is it defined based on the Diracs at the mi's or xi's?
Diracs at the mi's, thank you. Diracs at the mi's. Okay. And so our proof has 2 steps. So the first step, what we study is the expected number of critical points that project onto any particular set. So let me set what we call crit n of some set u in R4 to be the number of critical points. So the set of critical points of this tap free energy, so where the gradient is equal to 0, and that m projects into this set u. Now we're going to try to count this. And so what we show in the first step of our proof is that if I look at the expectation of the number of critical points that project onto u, this has an exponential upper bound. This is less than or equal to n times a certain complexity function. So it's n times the supremum over t in the set u of some function s star of t, and then plus some little o of n correction term for some s star that maps R4 to R. And I probably won't have... Okay, I'll see if I can give you a sense of what this function looks like at the end of the talk. Okay, our argument for this is using a Catch-Rice formula kind of argument. This was first done by Fyodorov in 2004 and made rigorous in a paper by Alfinger, Benarouz, and Cherney. And I'll try to give a little bit more detail about how this works, but let me first tell you what's the second step of the proof. Okay, so the sort of important but trivial observation is that if the supremum over t in this set u of this complexity function we define is actually negative, then what this means is that the expected number of critical points is exponentially small in n, which just by Markov's inequality means that with very high probability I don't have any critical points. So if this happens, then the number of critical points that project into this set U is equal to 0 with high probability. So the second step of our proof is that we analyze this complexity function. And so this is the part where we use lambda has to be larger than a constant. So for lambda bigger than lambda naught, there exists some set U in R4, it's depending on lambda, such that the following properties hold. So the first is that with high probability, if I have a critical point, so if the gradient of this tap energy at m is equal to 0, and the value of the energy is less than this threshold negative lambda squared over 3, then this in fact implies that this m has to project into my set U. So T of m belongs to U. The second property we want the set U to satisfy is the following, that so the second observation is that the global minimizer, let me call this m hat, of this tap free energy does satisfy this constraint with high probability. So it has that the value of the energy at this global minimizer is really less than negative lambda squared over 3 with high probability. And then we do an analysis of this complexity function on this set U that we defined. So the third property is that there exists a special point T star. I can call this Q star, phi star, A star, H star. This is an R4, where the complexity at this point T star, so S of T star, is actually just equal to 0. And if m were to project exactly onto this point T star, then we achieve the optimal Bayes error. So, and this quantity that I wrote up here, 1 plus Q star squared minus 2m star squared, is actually exactly equal to this optimal Bayes risk of lambda. And then finally, we have this quantitative statement that for any epsilon greater than 0, if I look at what is the maximum value of this complexity function s of t, so sup s of t, where t does belong to U, but t is not close to t star or minus t star. So the distance from t to t star is bigger than epsilon. And by a sign symmetry, I need to also restrict t to minus t star is bigger than epsilon, that this is actually negative.
Is S related to S star?
Yeah, S is just S star. Okay, so what these together means is the following, right? So the picture that this paints is the following. I want to look at critical points of my tap free energy where the energy value is less than this threshold. And what we show is that, so first of all, the global minimizer does satisfy this, so there's at least one such point. Any such point has to project into this set U in R4, where we can use step 1 of our proof to understand that basically everywhere in this set, there's probability 0 of having a critical point there, except for in an arbitrarily small neighborhood of some special point T star and actually minus T star as well. So there exists T star. This also holds for minus T star. Right, so there are these two special points which are really the global minimizers of my function, or they project there. And so for an arbitrarily small neighborhood, we can show that as n goes to infinity, any critical point which satisfies this condition then must fall into this arbitrarily small neighborhood of T star minus T star. So that makes sense.
Also, can you give some intuition? Why do you expect so many critical points? It seems like very such a.
Why do we have, for example, possibly an exponentially large number of critical points?
Because it's like QM is very simple, right?
I don't have much of an intuition for that. I mean, I think it's known for these kinds of models that, I mean, our sample is at n, you know, n is, okay, n is what it is. I don't know, I don't have much intuition. But I think at low energy levels, they don't have, actually, so the belief is that there's only this one critical point at the low enough energy level. But for high enough energy levels, we believe this landscape is quite rough.
The complexity come from the both terms or one of them?
The complexity function here?
Yeah.
What do you mean by both?
I mean, complexity of the critical points, that you have so many critical points.
Yeah.
I mean, that basically is the critical points are, you have the term up there, right? 1 plus QM squared minus 2.
No, so this is just if I were to have some point m, the risk, the loss that's achieved by this estimator defined by m is this particular function of m, and what we're showing is that there's a particular point where this loss is exactly the Bayes risk. In the neighborhood of this point is sort of where we expect all of the critical points beyond a certain energy level, and so they're all good enough to achieve the optimal Bayes risk. And outside of this neighborhood, at least up to this larger set U, there are no more critical points there. That's the calculation. Okay. How long do we have time, John?
About 0 minutes left.
About 0 minutes. All right, I'll stop here.
Give or take.
Okay, I was gonna. Okay, that's fine.
Okay.
I'll stop here.
Questions?
So if you change the prior, the after energy would be something different, but the theorem should still
So you can change the prior. The tap-free energy would be different. I actually think that does work. I mean, because you're familiar with these AMP kind of arguments.
the rationale. I don't get the intuition. Is it because of the replica symmetry?
That-
Everything, all the globals in either of these energy shift.
Also, we're in a Bayesian inference setting, so it is replica symmetric.
Yeah, so I'm saying it's because of that, or there's something more.
It's because of that we believe the global minimizer of the tap-free energy should correspond to the Bayes posterior. Not just for this prior, but for other priors. But the specific form of what the correction in the tap energy should look like, you would have to work out.
It's just pink.
Yeah, Levi.
Is this method equivalent to some variational inference with some family of possible distributions other than mean field?
Can you repeat the question?
Yeah, what was the question was, is this method equivalent to some other form of variational inference with some other family of distributions other than mean field? Let me rephrase your question as maybe, is this equivalent to making an approximation to the posterior that's not a product law? Is that what you're asking? No, I don't think so, because at the end of the day, this is still, the approximation we're making is still some kind of a product approximation. The product approximation is correct at the level of low-dimensional marginals.
But I think the question is maybe the correction term appears if you, it's a very complicated question. You can imagine a prior, posterior that gives you the correction term. You came about the correction term in a very intuitive way, but you can't just come about it by imposing it on the prior.
Is that the question?
Yeah. I feel that's...
So if you
it's
take,
possible, right? In principle, it's possible you get the correction term and then another posterior.
I don't know what it means to get it from the prior. I mean, once you have the prior...
From the posterior. You impose the posterior forward, right?
No, well, the posterior is going to come from the prior. The posterior is just going to come from this prior, whatever that gives me is some posterior. I can write down the KL divergence for that posterior, and then we add a correction term on top of that KL divergence. So it is still a product approximation in some sense, because of the, we're trying to compute the expectation of a second moment of x. So this is really the product, it's a property of two-dimensional marginal distributions of this x, which are correctly, roughly independent. So that's still, in some sense, the right approximation that we want to make, at least for a model like this. But because of the fact that we're estimating a high-dimensional parameter vector, there's some kind of a global interaction between these variables that we want to account for when writing down this carry.
Suppose you made a different approximation of the posterior, say like that it's a tree structured posterior or some kind of combination of trees or something else that we often think of being able to do efficient inference in. Are we still going to have substantial problems? Is it possible this fixes some of these issues?
Yeah, you can change the model, right? So for example, if I were to consider instead of this Gaussian noise, which kind of
instead of a mean field approximation, we made
where would your tree structure come from? I mean, our prior is just independent.
Well, the posterior is not independent.
The posterior is not independent. So you would get some kind of a tree structure in the posterior, I think, if your likelihood, like you're instead of having
you're
this
approximating the posterior with the mean field, right?
Yeah, so okay, so let's say
approximate the posterior with some kind of beta approximation or tree approximation, or I don't know, some alternative approximation to the mean field.
Maybe we can talk about this offline. I mean, I think you'll get a tree structure in the posterior if like your likelihood of variables x have some kind of a sparse interaction structure.
Not the true posterior.
Okay.
I mean, you made a mean field approximation.
Yes.
instead of mean field, make a different approximation.
It's the same question that they asked them.
But it's still going to just be problematic. No, I don't want to recover tap. I want to just do something completely different.
Sure. I don't know how you.
Okay. Well, we now have a break until I don't know when. Until we ring the bell, I think. So.